n. So you know the complexity of the quicksort in all the cases. So in best case and average case, we consider that the complexity is order of n log n, but in worst case, the complexity is order of n square. Okay, now so only 10 responses I've received. Okay. So these are the answer. You are Tn to Tn by 2 plus n is the best. N plus n. So, okay. So yeah, someone is writing the complexity here. N log n best case. Okay, n square is worst case. Okay. But I am asking the recurrence relation here. So n log n square best case is Tn by 2. Okay, correct. Yeah, so this one is 2Tn by 2 plus 1. Yeah, this is not correct. Tn by 2 plus n minus n. Okay. 2Tn by 2 to drop and multiply. Okay, this is not a correct representation. Between, okay, best case, and this is the best case. Okay, so okay, let's discuss this. So for quick sort, we have already seen one question. What is the worst situation for the quick sort is? What is the best situation for the best quick sort is? So for best case, our problem is always divided into two halves if our pivot comes in between. So Tn will always divide it like this, Tn by 2 and Tn by 2. Okay. We call our quicksort recursively on each left part before the pivot and each right part after the pivot recursively. So every time we call quicksort 2 times. So our function in the best case, for the best case, our recurrence relation will be Tn equal to 2 into 2Tn by 2. Okay, plus, but every time we are performing one partition process before this division part. Okay, so this partition takes order of n times. Okay, because we select the exact position of the pivot element using this partition method. So this partition takes order of n times. Yeah.
Sir, but we usually keep the partition always the same, right? Like we will always keep taking, suppose, the first element or the second, like.
But
So shouldn't it be over?
But after selecting pivot element, we just assume that this is the pivot element. So we just consider that the first element as a pivot. But after selecting the pivot, we find out the exact position of pivot in our list. So that that operation performed by the partition method.
Okay, so it's kind of like n by 2. I have to bring it to the center. So when we, put the smaller elements on the left and bigger elements on the right.
Yes,
so
yes, yes. So this partition operation perform this operation. So basically, we all elements which are lesser than this pivot elements come before, and greater than come after.
Got it, sir. It's a linear comparison.
So we have to traverse all the element and compare all the element by this pivot element.
Yes.
So this takes order of n times. So this is the order of n part which we will perform for every recurrence for every call. This is the recurrence relation for best case. Okay. So our hierarchical representation like this, n by 4 and Tn by 4 again, like this. Okay. So in that case, what will be the complexity is? So n, this is step, so this is n steps, so like this. So total. So what will be the height of this tree will be log n, and so we can perform this n plus log n time. So this is n log n. But what happened in the worst case? So in worst case, if we are selecting pivot as a first element, and after performing this partition method, and our pivot element come into our one side. So every time we have to call the quicksort algorithm on n minus one elements. So for example, so like this. So we are starting from Tn elements, and every time we have to call our recursive solution is Tn minus 1 plus order of n. So we can draw the diagram for this Tn, and our pivot element, for example, come at the first position, and then we have to call our recursive quicksort on the right part of that. Okay, so Tn minus 1 we have to call. Then once again, for example, our pivot comes at the first position, so we have to call again Tn minus 2.
Sir, you have directly written Tn is equal to Tn minus 1, but algorithm wise, we use the same algorithm for the best and the worst case, right?
Yes. So we have to use the same algorithm. No? So we have to
like how is Tn minus 1 came out of that?
So this is the actually worst case situation, Tn minus 1. So this will come by the same algorithms in the worst case.
Okay, like the list, like if we can say like the list is already sorted.
List is already sorted, and we are selecting. So for example, 1, 2, 3, 4 like this. Okay.
Okay,
this
but
is the input list. So we are selecting this is a pivot element. So this element will come at the first position, and remaining element will be 2, 3, 4, 5. So we will call the quicksort algorithm. So we will call. So there is no left part. Okay, before the pivot, but there is a part after the pivot. So this is the n minus 1 element part.
And this on is constant, like for finding the position of that.
Yes. So this is the same. This is the same partition process. So we will perform partition completely. Na? So we will have to compare all the elements by the pivot element. So it will take the order of n times. 1 second. Exit. Okay. Yeah. So this hierarchical representation become like this: Tn minus 3 dot T1. Okay. So the total number of labels will be n in that case. So here n, here n minus 1. So same situation, and every step will take n times used by the partition method. So like this, and height is n. So the sum of n plus n plus n dot n times equal to n square. So this is the complexity. Okay, next question. We are moving to this one. Okay, this is also an important question. So now we are moving to the linked list part in the big three. Okay, Abhishek Gupta. Okay. So Abhishek, you can join on the peer deck, and you can also
now also I can join.
Hello.
I'm asking.
Yes.
Now also I can join, right?
Yes, you can also join. I'm just sending the link.
Okay.
Yes, so I have sent the link in the chat box. You can join the peer deck. Okay. So So here one implementation is given of the queue using the linked list, and there is one structure is given for the linked list implementation. So here we have 2 pointers, head and tail. Yeah, so there are 2 pointers we are using, head and tail. Head contain the address of the first element of the linked list, and tail contain the address of last element of the linked list. And every node contain the address of next element in the linked list. Okay, so this is the structure of the linked list, and every node is created by this class node, and each node contain these 2 fields, self dot data, self dot next. Okay, so data contains the actual data, and next contains the reference of the next node. And we are implementing our queue using this linked list structure, and we are performing our 2 operation in queue and dequeue for the queue. So what we are doing in the in queue, that in queue we implemented by inserting a new node at the tail. Okay, so in queue means we are inserting a new element in the queue. So we can insert the new element from one end. So we are inserting the new element in the last position of the linked list. Okay, and in dequeue, so dequeue operation basically perform to delete one element from the other end. So we are performing this operation in the linked list by deletion of a node from the head position. And if so, we consider we are removing the first element from the linked list. So what will be the complexity? Best complexity, we can say that to perform this operation for in-queue and dequeue. Okay, so I have already 13 response I have received. 15. Okay, so 15 response. Oh, also from this time it's combined. A is 7, B is 1, C is also 6. Okay, and D is 1. So A and C are the confusion point, confusion option. Okay, A and C. So you can see that in the linked list structure, we have 2 pointer. Head that contains the address of the first element, tail contains the address of last element. So for removing the element, so we are inserting an element at the last position. So for example, if we have a list, so here if we draw one list structure. Like this. So we have a head, and every something like this, and there is also one more pointer, tail, that contain the address of last. Okay, so for in-queue operation, we are inserting a new node in the last position. So for insertion operation, so we can perform this operation in constant time because we have 2 pointers. First is head that contains the address of first element, and tail that contains the address of last element. So for inserting a new node at the last position, only we have to require that we have to set, for example, if we want to insert one new node, so we have to set, we have to update some address. So we have to set here what will be the value of in this field is none, because there is no node before that. So we will update that tail dot next. So tail is representing, tail is referring to the last node. Okay, and we want to insert one new node after that. So we simply write that tail dot next equal to, for example, the reference for this node is new node. Okay, so we simply write that new node. Okay, so this link will created. After that, we have to mention that this is a last node. Okay, so we will we will initialize the none value in this field. Okay, so new node dot next equal to none, and after that we have to change the reference of tail. Now after adding the new node in the last position, so this should be the last. Okay, so we will change that tail equal to new node. Okay, so using these three updation, we can add new element in the last position. So this is the constant time. Actually, we are not traversing the list, we are not traversing each node. We can directly inserting a new node at the last position using this tail reference. Same for the remove operation, DQ operation. So this is a constant time, so this will take the order of 1. Same for the remove DQ operation, we want to remove first element from the list. So for the first remove the first element, so we have to change the reference of the head only. Okay, so we will just change that head equal to head head dot. So head is referring to this node, and the next node address is placed in this field. Okay, first node next field. So we can simply write the head dot next. So after that, the reference of this node will be assigned to this node head using this line. So this will be linked here. Okay, so both operation we can perform in order of 1 time. Complexity is order of 1 time. So option A is correct for that question.
Sir, I have one doubt here. Not in this question, but when we have a pointer which is pointing, like which is taking the value of head, so then what we consider it like it is just a pointer who is
only. So you said that you have only one pointer that contains the address of first element.
No. I'm not saying like there is a complete linked list. Whatever be the length you want to consider, maybe 5, maybe 6, or whatever be the length. And we have a head which is just a pointer of the first element.
Okay.
We have taken one pointer and stored it, assigned it equal to head. So what does that pointer contains? Whether the address of the first element or just the first node?
Actually, I think you are talking about the implementation which is taught in the lecture, where we are using the recursive approach to implement these things. So according to that implementation, so what we are doing is so we are just creating a, for example, a equal to class so node linked list. So what I don't know what is the exact name of that class. So for example, a linked list. We are creating a one object linked list, and we are also assigning some value. So in that case, we are creating a object for this class. So same times one node is also created, and we are considering that this A is a reference of that first node. After that, we are recursively call this same class. So we are just adding inside this. So initially using the self dot same thing, self dot next equal to the next node we are creating.
Yes, sometimes we go to next dot next.
Yeah, next dot next. So same thing. So self dot next. So what is the meaning of this next dot next is? So for example, if we want to access the second element address, no, not the second element, next dot next. So okay, I have to see the implementer which you are talking about.
No, don't take the implementer. Just take one list. Let's say 1 to 5.
Okay. So I'm just creating a new head. This is head. This is 5. Example 6. 2. Like this?
Yeah, like this.
Okay.
Just take the 5 elements.
5 elements. Okay.
So when we we have pointer 1 which is pointing just to head, So that contains 5, right?
Yeah. So not 5,
Just
not
the
5.
address.
This contain the reference of whole this node.
Okay. We have a
Not 5.
second pointer 1, which contains head dot next. Then it will 5. Okay. Right?
Head dot next. So
Yeah.
actually head dot next, what is representing this? So we are reading the value from this field.
Yeah.
So that is not a separate pointer. Basically, we are using this. We are accessing the value from this field, head dot next. So head is referring to this node completely. So there are two field for every node, which for one is data, the second is next. So
Yeah.
we can read this field using this head dot next. Next, if we are assigning this for any value, for example p, so that means we are assigning a reference of second node in this
Okay.
p.
And when we have head dot next, then we are talking about the
So
2.
for example, yes, if you are mentioning that this next, so that means this part is referring to this node, and
Yeah.
dot next is referring to this address.
So for
Okay.
the
So
previous
this is the address of our second element.
yeah, for the previous example, this is what we have to do while deleting the head.
So previous example, so
Like
deleting the head, no? So yes,
Yes,
we are doing this now. So head equal to head dot next.
okay.
So we are just taking the address from this field, first node, next field. So
Okay.
what is the address? This address is representing to this second node. No? So we are directly assigning this address to head.
Okay. That's
Okay,
how we
so-
don't do head dot next dot text. No,
Yes,
right?
yes. Okay. So one more question from my side here. For example, we have a list head, and our list structure is this. Like this time we have only 1 point. Okay, this is null. Now the insertion. What will be the complexity to insert a new node at the first position?
That will be an constant 1.
Constant one.
Yeah.
Correct. Yeah, correct. Okay, I'm just taking one more example at tail. So this is also containing address of this last node. Okay, so you are correct. And insertion a new node at the last position. This is also a order of 1.
Yeah. Now in this case, it's 1.
Yeah, we have already seen. And now if we are talking about the delete operation. So if we want to delete the node from the first position, we have already seen this is also a 1. If we want to remove one node from the first position, what will be the complexity?
So order of 1.
Yeah, order of 1. Yeah, correct. We have seen previously. Now tell me what will be the complexity to remove the last node? Remove last node.
Order of 1, right?
Okay. Other one.
N.
So okay. Second answer is order of n. Okay, so why you are assuming that the removing operation can be performed in order of 1 times?
Because we have to just shift the tail to the previous pointer, right? Tail is equal to.
So
Yeah,
how you
because
can
we-
access? Yeah, how you can access the reference of the previous node?
Okay.
Because every
Yeah,
node contain the
I
every node contain the reference of the next node. You cannot traverse in the reverse direction.
Okay. Okay. Yeah.
Okay, so for removing the last node, so you have to assign the value in this field like none, and you have to change the reference for this tail also.
Okay. Okay.
So these
Yeah,
are
yeah.
operations required. But
Okay.
for doing this, we have to identify the reference of this node, second last node. So we cannot identify the reference of second last node directly. So we have to traverse the list from starting.
Yeah.
Okay. So in that case, this operation can be performed in order of n times. So this is
If it is a
What is the
if
answer?
doubly linked list, then it will be order of 1, right?
sorry, can you repeat?
If it is a doubly linked list.
Yeah, if it is a doubly linked list, then you can perform this in order of 1.
Fine.
Okay.
So
What
because
is
this
doubly linked list?
doubly linked list is where each node contains the address of next node as well as the previous node. So for example, head, this is the head pointer, and the node structure is like this. So there are 3 fields for each node. First is data, and one is next, and one is previous. Okay, and that means every node contains the reference of the next node as well as the previous node. So we can represent like this. So this is the structure of the doubly linked list. Okay. So in that case, you can traverse the linked list in any direction. You can move from first to last, and you can traverse from last to first using this previous address. So in that case, you can remove last element directly, because you can find the address of second last element by this field, previous field. Okay, so you can find the address of second last element by reading this value, and after that you have to just send the none value here and just tail to here.
So then what is the answer to this question?
So in the previous question, actually we are using the singly linked list structure. So are you asking the answer for question which we are using?
For the question on the POD.
Yes. So this one is answer is A.
Sir, are we using here the doubly linked list?
No. But here we are performing 2 operations. We are performing insert operation at the last position. Okay. So that operation can be performed in order of 1 time. And we are performing one delete operation from the first position. So that operation is also can be performed in order of 1 time. But remove the element from the last position in this structure cannot be performed in order of 1 time. That will be performed. That will take the order of 1 time.
So, sir, we are making a new class Q in which we are keeping track of the head one, head node, and the tail node.
Mm-hmm.
And in the tail node, we are adding that the new node which we are which we are adding.
Yes.
Thanks.
Okay. So next question is so this is based on the queue and stack structure. We know that what is the queue is and what is the stack is. So queue is perform the operation like first in last in first. Sorry. What is this? First in first out. Yeah, first in first out based operation. So those elements will be inserted first, will be removed first. So these are the operation in queue and DQ for the queue we are performing here. So in queue is performing the insert operation, and DQ is performing the remove operation from the queue. So tell me what will be the sequence of value removed from the queue by DQ operation H. So in the queue structure, we perform both operations from the different ends. If we are inserting the new element from the last position, so we will remove the element from the first position. Okay, so that is the structure of the queue. So should remember these things. And what will be the output? So total 10, 11 response have received 12. Okay. Okay, now 14 is there. So let's see. So options, most of the answer is 30. Okay, option C. Okay, let's look. Okay, option C. So first we are inserting 10, then 20 will be insert after that 10. Then we are performing DQ operation. So 10 will be removed. Okay, correct. Then we are performing NQ operation again. So now sequence will be 20, 10, 20. So next element will be removed 20, then 10. Okay, 20, then 10. After that, we are performing DQ 3 times. Okay, we are performing. Okay, so 20 will be removed. And after that, we are performing 20 in Q and DQ. 20. Yeah, so option C is correct. And this is based on the stack. So quickly reply on that. So stack is basically perform the last in first out operation, and we perform this operation only from one end. Never list or linked list. You can use any. Okay, so I've received 17. Okay, so most of the answer is B, correct. So where is the answer? So push 10, 20, then 20 will be removed first, then we will insert 10, 20, then 20 will be removed. So B 20, 20, then 10, and then one more 10, then post 20. Yeah, okay, so B is correct. Okay, so this question is about the hashing concept. Here we are using the linear probing approach. If the any index is already occupied before that, so we will check the next slot to find the free slot. So this is the approach in linear probing. So here we are asking the what index would the key value 145 be inserted. So if we are inserting these keys 56, 166, 80, 16, 145 in the same order. So what will be the index for 145 will be using this linear probing approach. Only 6 responses I have received. So 56, 166. Okay, just marking the numbers. 56, 166, 80, 16, 145. Okay, 7 response. Okay, so we are taking the so 4, 5, 4, 4, 4, 4, 2, 4. Okay, so most of the answer are 4. One is 5, one is 2, and one more is 5. Okay, so we are asking the index here, and we have 10 buckets, 0 to 9. So we have index like this: 0, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9. For our hash function is k mod 11. Okay. And first we will check for the 56. So 56 mod 11 will be 1. So 56 will be inserted at here. So remaining value is 1. So 56. Now 166 will return 5, save 1 value. Now the 166 will save here. Okay, so yeah, 166 mod 11 is returning 1, but 1 is already occupied. So we will check the next empty location. So we will check the second slot, second index slot. So that is empty. So we will save this value here. And 80, so it will return 3. Okay, so 3 is already empty. So we will save directly here. And now 16 will return 5. 5 is already empty. So it will save here. Now 145. So 11, 35, 2 will return 2. Okay, 2 is already occupied. Then we will check the next slot. It is already occupied. Then we will check the next slot. Yeah, 4 is available. So we will store this 145 here. So answer is 4. Sir, honored YouTube, this session has started recorded for just 50 minutes. Where the session has started. Yeah, Harshal, actually will look this. I don't know what happened from the backend team.
Sir,
Yes.
I have a small doubt. If K mode 11 is supposed to be in 5, so we already have 4 in our hash table. Do we need to check the next one or the previous one?
So what value you are taking?
We already have a space in hash table in
Yes,
4,
yes.
but
Okay.
we got K mode 11 is 5, but already that is already stored.
Yeah, no. So we will check the next slot always.
Next node. Okay. Okay. Thank you.
Okay. Yeah. Okay. So yeah, next question is based on the graph. So you have already seen the DFS algorithm. DFS in the week 4. Suppose we obtain the following DFS tree rooted at node G for an undirected graph with vertices A to K. Which of the following cannot be an edge in the original graph? So this is a MSQ type question. So you can write your answer like A, B in that form. So we are performing DFS on the graph, and this tree is created as a DFS tree by the DFS traversal for a graph. So which of the following edges or edges are not possible in the original graph? Okay, so my response I received B and D, B and D, A and C, B and C, B, D. Over. C, D, B, D, A, C, D, E, D, A, O. So no common answers, only B and D is repeated 3-4 times. Okay. Yeah. So in the original, if we see this tree, DFS tree, this is a DFS tree. So we can check each option one by one. So first option is D, G, D, G. Okay. So for example, if D and G are connected in the original graph, so is it possible? 1 second. Which of the following cannot be arranged in the original? We are performing DFS. A is D and G. D and G. So is K. Cannot be. Okay, so we are asking the cannot. Yeah. So this is possible. D and G is possible because so for example, if we are starting from G. So we will check. We will traverse one adjacent first. For example, if we have traversed from G to K, then we will complete the depth first. So we will check the next depth level from the K. So K to F we can move. If there is no next adjacent is available, so we will move back to the K and then move to the next different depth. So we are moving here K to D. So if G and D is connected in the original graph, so their T will remain the same. Okay, so there is no affected in the traversal tree because we have already traversed G, so we will not move back to D to G here, and that edge is also will not the part of this traversal tree. Okay, so this D and G is possible. F, D. F,
Sir,
D.
sorry to interrupt you, but in
Yes.
generally when we talk about DFS, we generally don't go by the like order. Do we assume that or not?
Sorry, I'm not getting. Can you repeat first?
We generally follow some order, right?
Order. Okay. Actually, if any implementation is given,
Okay.
if in the question, if any implementation is given, so you have to follow the implementation. But if implementation is not given, so you should follow the concept of DFS and BFS also. So what is the concept of BFS and DFS? So in DFS, we always traverse the depth first.
Yeah.
Okay. After that, we will come back and then choose the next different depth. Come. Okay. So this is the concept. So we will not check these things we will not check any order of the like I's come before K, like these things.
Okay.
Okay. We will just check the concept. So here, if D and G is connected, so definitely that will not be the part of the tree, and there is no effect in the tree. So DG is possible. F, comma D. So for example, F and D are connected by an H. So when we are starting from G to K, so if we are starting from G to K, then K to F. Okay, so this is the first depth. If F and D is connected, then this D will come. D will come down this F in our traversal tree. Okay, if F and D is connected, so we will traverse D after the F. So this D will D should become below this F like this. So this is not possible in the original graph F comma D. Next is A comma I. So A, where is A? A is the below side and I. Okay, so this is also A comma I. Okay, so A I. Yeah, H J A. Yeah, this is also possible because A and I is connected. So definitely, if we have traversed the A using this path I to H to J to A, so we will not traverse this I again. So we can skip this S, and this will not be a part of this tree. So C is also a possible option. So currently now the correct answer is B according to the question. We are asking the cannot be. Okay. So first is possible, C is possible, and D, C comma B. So C comma B here. Okay. So if C and B is connected, so we will traverse like this: I to H to C. Then we will traverse B if there is an S in that are connecting to C to B. So this tree should like this because we will complete the depth. If C to B is connected, so after C we will traverse the B directly. Okay, so this is not possible. So correct answer now according to the question is D. And last option is E comma H. So E comma H, yeah, so same things. E and H is connected, so there is no change on the traversal tree, and we will not traverse the H again. Yeah, so the correct answer is B and D option are not possible in the original graph. Other may be possible. And next question is similar to this. So here we are asking the BFS things. Now we are performing BFS on this tree, and same things we are asking that which of the following cannot be edge in the original graph. Okay, so 7 response, 8 response. Okay. ACE. So we are asking here cannot be possible. Okay, so this should be confirmed by you. ACE, ACE, ACD, ACE, AC, DG, CB, EH. Okay, you have mentioned the answer. BD, AB, ACE, ACE. So most of the answer are ACE. Okay, let's check. Okay, so first see the DG option here. So DG in the BFS, what is the concept of BFS traversal is we always traverse the first adjacent level, then we will move to the next adjacent level. Okay, if we are starting from the G, so we will always traverse all the adjacent of G first, then we will move to the next adjacent leaf. So here, if DG is connected, so this is not possible, because if DG is connected, so our tree should like this: G, K, D, and I, like this. Okay, so all adjacent nodes should be come on the same level. If DG is connected, so this D should become like this. This is not possible in the traversal. AF comma D, so there is one correct answer is A. Now AF comma D, so AF comma D. Okay, so F and D is connected. So here, okay. So if F and D is connected, so that is creating a cycle. So we will ignore these things, because we have already traversed this D from K, because this D is also adjacent of K. So if F and D is there any edge, so we will ignore this edge. That will not be the part of our graph. So this is possible. AI, so A and I. Okay, same things. So C option, if AI is connected, so our tree should be like this: H and A and B. Like so, all adjacent vertices of I should be visited first. So this A should become at the H and B level. So C is also correct. And CB, so CB, okay, if CB is an edge, so that this is also a back edge and creating a cycle. So this is also possible, because if we are traversing all adjacent of I, if all adjacent of I is H and B, so is there any edge available with C and B? So we definitely, this will not be a part of our tree, and this will be ignored, because we have already traversed all the adjacent of I. Then we will move to the H, and then we will traverse C. So we will not traverse B again, because we have already traversed from the I. So this option is possible D. Now next is EH. So EH, yes. So same things. If EH is an H, so this should be like C, E, and J. So E should become at the same level to the C and J. So A, C, E, these three options are correct according to this question. Okay.
So can you explain that C and B wala? Yeah, C.
C, sorry, which one? C and B.
Yeah, that is option D. That I mean option D.
Option D, CB. Okay.
Yeah.
So CB, if we are connecting this CB, so what will be happen? CB is connected, and B is also connected from the I. Okay, so we will traverse the B from I first, because the adjacent of I is H and B. So we will traverse the H first, then B first. After that, if there is an, we will traverse all the adjacent of H. So this is C and J. Okay, and so when we move to this C, and is there any edge available to C to B? But B have already traversed, so we will not traverse, and we will ignore this edge, because this is creating a
there is if I can say, like there is a kind of a pattern, like
pattern is because we are performing adjacent level first here, no? BFS traverse, we traverse adjacent level first.
Yeah, that is fine, but like only children's can be, like they can be connected, like grandchildren's can't be connected. It's like something like that.
Yes, grandchildren cannot be connected. Yeah.
Okay.
Yeah. So C and B can be connected in original graph, so that this edge will not consider as in a traversal.
Fine.
Okay. So yeah, next one is this.
Sir, what was the final answer for that question?
ACE.
Got it, sir.
Okay. So this is the complexity to find adjacent vertices in adjacency matrix and adjacency list respectively. So for example, if we want to find the which nodes are adjacent of any nodes, and we have two representation of graph, adjacency matrix and adjacency list. So what will be the complexity to find this? So you know that we represent adjacency matrix using the matrix forms, either using NumPy or nested list, and we implement this adjacency list using dictionary. Okay, so 8 responses I have received. So we used these things in our implementation BFS and DFS to find the adjacent nodes. So we can, so in dictionary, in adjacency list, we can directly find out. So the answer A and D is the most selected option. Okay, 5 and 5. Okay, so A and D. Oh, sorry. I mentioned all options are A here. Okay, so A and D, that means last options. Okay. So which one is correct? So in adjacency matrix, what is our representation is that? So for example, if we have a 5 node, okay, so we represent like this, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, okay, row and column combination. If is there any edge available from, so this is represent to I and this is represent to J. Okay, so we just consider that if is there any edge available from I to J, so we mark 1, otherwise 0. Okay, so if for example, if edge is available 0 to 1 edge is available, 3 edge is available, and remaining are 0, like this. So 1, 2, we will fill like this. Okay, so this is the adjacency matrix representation for the graph. So for finding out the adjacent nodes for any node, so we have to traverse all columns. So for example, if we want to find what are the adjacent nodes of 0 is, so we will check that this row, 0th row, and we will traverse all the columns. Okay, so we will just A0. So we will perform this like this J, and J will be start from 0 to 4. So we have to check only A0, 0, A01, A02, A03, A04. So we consider, so this is representing the n, total number of vertices in our graph. So the complexity of finding the adjacent node is here order of n. But in the case of adjacency list, what is the representation of adjacency list is? We represent in the dictionary. So for example, D, so we represent like this. So 0, for we represent a list. So for example, 1, 3. So for 1, like this, 2, 4, in that way. So this representation directly represent that what are the edges available from this source 0. 0 to 1 there is one edge, 0 to 3 there is one edge. So we can directly find out this information in constant time in our dictionary. So we directly check the list of this 0 key and we will find the all adjacent vertices as a value.
But we have to, if we have to find the like particular, like then we have to transverse n time.
No, so but here we are asking to find out the vertices, this information only.
No,
I don't know how many adjacents are there as a value. So we will get this information from the dictionary in constant time.
no, but we have as a value we have a list, right? So
Yes,
then we have to transfer this list. Like we have to go to the first 0th position, find, and we have to find like we will take 1, then to first position, and then we will take 3, like that.
So here what we are questioning is which of the following is represented the combination to find adjacent vertices in adjacency matrix and this. So here actually we are getting this information list. So after that there is no information given what we are doing these adjacent nodes. Okay, so we have what operation we are performing with these nodes. So but we are getting this information in constant time. Here we are just finding out which nodes are adjacent of this. So we are getting this list in constant time.
Okay, you are talking about only this list.
Yeah, so we are getting this information list.
So
the question is like for one particular node, what is the adjacent vertices, right? That's why the adjacent matrix comes of order of n and it is order generally. Yes. Okay, the meaning is like that. Okay. Otherwise, it will be order of n square.
And
so one particular node, we are finding the adjacent vertices. So it is coming as order of n, right?
Oh, I think this is not given. Now find adjacency vertices. Okay, of node is what is missing because of that. Okay. Yeah. Here we are asking to find the adjacent node for any particular node. Okay. So there is one more question about the complexity here. So here we are asking the same things. The representation is adjacency list and graph is directed graph. And here we are asking the number of incoming edge. For each vertex V, we want to compute the set of incoming edge U, V. Here we are asking for each vertex. Okay, so option C is correct. Yeah, so n plus m. So for incoming edge, we have to traverse all the values actually. And for traversing all the values, we have to traverse all the keys. So because of that, so values is representing basically number of edge. So here m is representing the number of edge and n is representing number of vertices. So that is representing the key in our dictionary. So for incoming total all incoming edge, we have to traverse all the values that is representing the incoming edge. So the answer is C for this. I think option is not. All option is visible to you for this question.
So the last option is hidden by the bar on the bottom.
Okay.
Here deck all the options are visible.
It's transparent, so it's visible.
Okay, so mark the answer for that. Which of the following is our possible possible DFS traversal. So here implementation is not given. So just use the concept of DFS. Don't think about the stack things or these things, exact implementation. Order of elements. Don't think about the order of numbering, yeah, like this, alphabets order. Just check the concept.
Sir, here also we can't take the order. Like if you go through the questions.
A depth for search is started at node A. The node are listed in the order they are first visited. Which of the following is a possible output? Yeah, so here in the option, we are given the order in which
we have to
we
go
are
through options only. Like that is the only options we have. Otherwise, it would have been different.
No, you just check. You have to check only the option order is correct according to DFS concept or not. So just check each option because multiple traversal order are possible. Okay, so 11 responses received. C A C D C A A C B A C B A C D A C D A C. Okay, so first check the A option A B E G H F. So if we are starting from A, we can move to B. Okay, then B to E. Yes, we can move. And E to G. Okay, we can move E to G H and then F. Okay, the first option is correct. We are just traversing the depth according to the adjacent node. So next option is ABF, ABF. Okay, E, yeah. So from F, so if we are reaching at F, so ABF, we cannot directly traverse E here because we have to complete the depth first. So we can move from F to H as well as the G also, but here we are moving to the E. This is not possible depth first. So B is not correct. And C option is ABF, ABF, H, G, and E. This is correct. So A, C is correct. Now A, last option is also not visible to me. Can anyone tell me what is the last option?
AFGHBE.
AFGHBE. So AFGHBE. Okay, this is also correct. So ACD is the correct answer. Okay, so this is this next. Here we are seeing here option D is also not available. So here we are asking the BFS traversal. In BFS, we traverse the adjacent first, then move to the next adjacent. So, okay, so 7 response I have received. Now AB, 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 yeah, AB, most of the answers are AB. Okay, let's see. So ABE, so A to B, E then F. Okay, HG. So then we will move to the next adjacent from BH and E. Okay, so this is correct. And ABF. So ABF is correct. E correct. HG. Okay, so this is also correct. And C option is ABF. ABF H. Yeah, so here we are leaving the E. So this is not possible because E is the adjacent of A. And last option is not visible to me.
Sir, it's the same. A, F, G, H, B, E.
A, F, G, H, B, A, F, G. Okay, so this is also not correct. So AB is the correct answer for that. Okay. So now this question is based on the topological concept. So this is time taking question. So first create the graph for that. After that, you can apply the topological sort concept on that graph, and you can find the correct answer. So we have slide links. Okay. Okay, I will share the PPT links, drive links on the discourse. If you want to access this person. Okay, so I have received the 7. Oh, so please tell the difficulty level of quiz is the question would be the same as the mock and the session. Yeah, so question difficulty level will be similar like to mock. Mock is also difficult compared to the quiz, and question will be similar like your graded assignments, your mock test. Also, some question I have taken from the last quiz term papers. So yeah, difficulty level will be same. You can solve these 15, 16 questions in 45 minutes, I think.
Sir, if we are able to solve whatever we are solving here in these slides, like, is it like, can we solve exam paper in a in a appropriate time?
Yes, you can solve.
Okay.
So 15 question, I think we consider that so some question are simple question. You can directly find out the answer without any calculation. So you can save some times on that question. So some other questions, some maybe takes 4 to 5 minutes. So that will be managed according to your speed and solving the questions. So I think 15, 16 questions easily can be solved in the 45 minutes.
And it will be same difficulty level, like
yes.
What we are solving right now, right?
Right now, yeah, some questions are very easy. I include like the first many questions, so I've included for the complexity.
Okay.
So yeah, the question will be similar like as a mock and graded assignment format.
Okay.
Okay, so this topic should be have to be focused. So you should focus more to week 2, 3, and 4. And I think the equal distribution is there. So 5 answer is 5, 8, 66, 7, 5, 5. Unable to communicate YouTube live play. Is there any way? So I think some technical issue is there. 6. Okay. First complete this question. So for solving this question, I think sir mention this type of things. This type of question where the requisite is given. So we can solve this type of question in using this topological sorting. So we can create a graph. Okay, we can create a directed graph. And so for example, if we start, so there are total 1 to 11 numbering is there. So we mark that one must be divided before room 3 and 4. So, okay, so 3 and 4. That means one we will graph like this. Okay, 2 must be divided before 6. So 6. For example, we are creating. So 3 must be divided before row 5. Okay, so 5. Don't know spaces available. Okay, so 5 must go. Something spaces. Can we separate this one? Okay, just wait. Okay, 3 to 5 and 2, 1.
Sir, 3 before 5 na?
Okay, let me check. So 3 must be divided before room. Okay, yeah, sorry. And so 5 must be divided before room 8 and 9. Eight and 9. And 6 must be divided before 7. So for 7, I can create this directly. 7 must be divided before 5. So, okay, so there is one edge. 8 must be divided before 10. And after that, 9 must be divided before 11. Okay, so this is the condition given as a prerequisite. So we can, so this is a tag actually. Okay, and we can, so there is one condition, we can start with the node which have in degree 0, and we can we can complete this task parallelly. Okay, so how many nodes are available with in degree 0 right now? So there are 2 nodes available. So in the first phase we will complete this. Okay, so 1 and 2 we will complete. After removing this part, so we will get 3 nodes, so we will remove these as, and the in degree of 3, 4 and 6 will become 0, and in the next step we will complete all these 3, 4 and 6. Okay, and after removing these 3, so in degree of 7 will become 0, but 5 will remain 1. So we will perform 7, and after removing this, and then we will perform 5, and after completing this we will perform 8 and 9, 8, 9, and then after removing this we will perform 10 and 11, and every takes 1, 2, 3, 4, 5, 6. So every parallel task takes 1 day. So total 6 days required to complete this task. Okay, so this is the way to solve this type of problem. Now next is this, this is basically properties based question of the graph. If you not remembering this property, so you can simply check this property after taking some few 2-3 examples, 2-3 or 4. You can verify these property by taking some examples. So which of the following statements are true about the undirected graph? Okay, 10 response I have received. A, B, C, E. Okay, A, B, C, E, A, B, one out in the old question index of 45 for mode 11. But why we are going for 4? Okay, so okay, so for this doubt, hashing doubt now, so yeah, this one, this one. Yeah, so for 145, actually we always start from that index where we are getting the index from hash function. So 145 mod 11, what value we are getting from this hash function? is 3, not 3, 2. So we will always try check after 2, not before 2. We always start to check after the index we are getting from the hash function. Okay, so we will check first 2, then we will increment by 1. Okay, so after the definition is also given, linear probing takes the original hash index and increment the value by 1 until a free slot is found. Because of that, we are checking the next condition after the index written by the hash function. Okay. So ABC, 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 AB, AEC, CD, AB, C. Combined option is there. Okay. So first option is the sum of the degree of all vertices is always even. Yeah, this is true because in the undirected graph, every edge contributes the 2 degree. Okay. So first for the each vertex. So definitely, so if edge, for example, if there are 5 edges, so definitely the total, it will create a 10 degree for the graphs. So the sum of the all degree will always be even. So this is true. The number of vertices with odd degree is always even. Yeah, this is also a true condition. You can verify this using taking some examples. Okay. So, and option C, in a complete graph, the degree of all vertices are equal. Yeah, so complete graph represented that when every vertices are connected by other vertices by n edge. So in that case, so degree of each vertex will be n minus 1. So if n vertex are there, so every vertex will be connected by n minus 1 vertices. So all degree will be same. C is also correct. A, C is correct. Now the sum of the degree of all vertex is always odd. So this condition is not true. So sum of the degree of all vertex is always odd. Yeah, this is not true. So you can simply verify this like, so for example, if you are taking like this, so here degree is 1, degree is yes, degree is 2, degree is 1. So the number of sum of this is 4. So B option will always be true for any example. So D option is opposite of that. So this is not correct. The number of vertices with an even degree is always even. So this can be identified. For example, if we have a one vertex like this. Okay, so for this graph, what we are saying that the number of vertices with an even degree. So even degree 2 now is even degree. Okay, so this is not the correct thing. Even degree.
It's a triangle.
Yeah, triangle is also correct. Yes. So this is 2, this is 2, this is 2. Yeah, both are even, but number of the even degree nodes is 3. Yeah. So you can verify or observe the correctness of the option using some example for this type of person. And next is the based on the same properties. We have an undirected graph with 7 vertices. We write down the degree of all vertices in G in descending order. Which of the following is a possible listing of the degrees? So here you can apply these properties. You can check the answer using the previous question property. Okay, just previous question answer is A, C. Okay. Okay, A, B, C. A, B, C is the correct answer for previous question. So
I'm not understanding the question. Can you repeat it again?
24.
Yeah.
Yeah. So here degree of each vertices are given. So we have a graph. We have a graph with 7 vertices, and degree of each vertices are given in the each option, and we are asking that which of the following is a possible listing of the degree in any graph, undirected graph.
Okay.
So this question can be solved by the properties of the previous question, correct property of the previous question. So there is no need to draw any graph of these type of degrees, so that will become much complicated. So you can simply apply the property of the previous question. If we see the property, the sum of the degree of all vertices is always even. So if you can sum all the, so 7 plus 30, 19, 24, 28, 30. So this is even. 18, 21, 23, 25, 20. This is also even. So 5, 3, 8, 3, 11, 13, 15, 16, 17. So this is not possible. Option C is not correct according to the first property. And 5, 3, 8, 11, 14, 17, 18. So this is also possible. So option C is rejected by the first property. After that, the number of vertices with odd degree is always even. So count the odd degree vertices. So here 7, 5, 1, 1, 4. This is correct. Here 3, 1. This is also correct. And C is all rejected. And here 1, 2, 3, 4, 5. Yeah. So here no 6. This is also correct according to second property. And next one is that is related to which of the following is a possible listing of the degree? So this is MCQ. One second. Yeah. Let's see. 7, 6, 6, so 7.
The MCQ is not working. That's why.
Yeah.
Hello, sir.
Yes.
Sir, the degree cannot be 7, right?
Sorry.
First vertices, the degree cannot be 7, right?
Degree cannot be 7. Yes. Yeah, first option is incorrect.
Yes.
Okay. But this is MCQ question. I think one more option to be incorrect. So 6, 6, 6. 3, 2, 3, 2, 2, 1. B, D, 3, 3, 3, 3. 5, 7.
In second option also, if 3 vertices are connected to other 6, so
yes,
like then other 6 means they should also have that number of degree.
Yes, yes. So yeah, correct. So if 3 vertices are connected to all vertices, so definitely other that nodes have a degree should be, I think, how we can verify this?
So the odd places, the degrees of the odd places are not summing up to even.
Odd places. So what you are saying?
6 plus 3 plus 2.
Odd places? No, we are not. There
Places,
is no
odd
rule.
vertices.
Yeah, so there is no rule according to like this order. Odd places. So there is one property is that the sum of the degree of all vertices is always even, and there is one also property, the number of vertices with odd degree is always even. The number of vertices with odd degree, this is also correct, EV always even. So what's this is incorrect. 6 if we are connecting the vertices, 16, 21, 12, 17, 18, property. Yeah, so if we are taking 6 in degree, 6 connection to the 7 vertices. So okay, so for example, 1, 2, 3, 4, 5, 6, 7. So if we connect the 3 vertices by everyone, and same for like this.
So can't we check the total number of edges that is possible as a rejection?
So
Number of edges.
So maximum number of s, maximum number of s can be n into
21 for
21.
undirected.
7 into 6 divided by 2.
21.
Yeah,
It should be
21.
So that can
Yeah.
also be a criteria.
Yes. Okay. So yeah, this is also correct thing. So yeah, B is incorrect, and now C option is incorrect. Now 5, 3, 8. So 12, 17. Okay, 20. Yeah, that is the correct things. Yeah, we can reject the option according to this.
But why C option is correct then? Okay, C is already rejected.
Yeah, already rejected by the total number of sum.
So only D is left out.
Now D is left. Yeah, so D is the correct answer. Okay, and the last question is this. Yeah, so consider undirected graph G. Let T be a depth first such traversal tree. Let U be a vertex in G, and let P be the next visited vertex after visiting U. So here we are just saying that we are visiting U, then just after we are visiting B. Okay. No. So let B be the next visited vertex after. Oh, yes. So we are visiting first U, then after that we are visiting B. Just after that. So which of the following statement is always true? So here leaf means, if you not introduce this term, so leaf means the last node. So after that you cannot traverse further. So that's called the leaf. So in this question, this must term, you should remember these things. Don't ignore this must term.
What is the previous question answer? I got disconnected. Sorry.
Okay, for this.
Yes.
So actually for the first option, 7 cannot be the degree of any nodes. Okay, this is incorrect.
Yeah. B
and
D.
option B is incorrect because the total number of edges are possible in the completed graph is 21. N into n plus 1 divided by 2. No. N to n minus 1 divided by 2.
Is 1 by 2, yeah.
Okay, so here the total number of edges is greater than this possible n. This is incorrect. C is incorrect because the sum of all the degree is odd. And then after D is remaining odd.
Okay, thank you.
Okay, so yeah, for this question, so 8. Okay, multiple option is also there. So A, B, C, D. So B and C is 3, 3, and A and D is 1, 1. Okay, so let's check. So for any particular graph, so I'm just creating one sample graph. So like this, A, B, C. So what is the G? Okay, so for example, if we traverse this graph, so this is the original graph, okay, G, and we are traversing this graph using a depth traverser from node A, for example. So what tree will be created for that is, so A we will traverse, then B. So I'm just creating a one possible tree, and we will show that how we can verify the option. So A, B, then D, then F, okay, then E, and so this is a undirected graph. So this is G, and then C. Okay, so this is one possible tree for this graph, and so first option, what is saying that if we consider that two. So what will be the order? So if we are just written the order for that is A, B, D, F, E, G, and C. Okay, so we can take any two adjacent vertices in the traversal order and verify this answer. Okay, so here we are saying that in the question, if U is just let U be a vertex in G and let B is the next visited vertex after U. Okay, so we can take any one of them. So for example, we are just taking D and F. So D, F, and yes, so this is a. So here option B is correct. But so what option A is saying that U comma V must be an edge. So that means if we are taking any two adjacent vertices, so there must be an edge between in these two vertices in original graph. But so this must condition is given, but here one option is there. So we are visiting this G and C. So we are visiting G first, then just after that we are visiting C. But there is no edge in between in the original graph. Okay, so this option C is valid in correcting. So making this option A and B incorrect. So there is one possibility is there. So UB must be an S. So this due to this must terms, option A is incorrect. Same things for the B. UB must be an S. No, this is also incorrect because of this C. And in option C, if UV is not an S. So here the condition is given if UV is not an S. So if U and V, so for in this case, UV is not an S. So definitely U is a leaf in T. So always in the tree, in the traversal tree, we will always back to the recursive call and then we will select the next depth path. So when you create any graph, any DFS tree, so like this, for example, if we are getting any DFS tree like this, C, E, F, G, like this. For example, this is a tree which is creating for any graph. So definitely when we are moving to F, so we will, so next traversal node will be G. So A to B, E, F. So there is no further node is available. Then we will back to the previous node and we will select the next different path. So after, so in traversal order, F, G will come after this F. Okay. So we can say that F is a leaf node in our traversal tree. So there is no path of no remaining vertices are available to visit after F. Because of that, we are moving back to the previous node and going to the next different path. So in that case, in the original case, so there is a chance, so there is no edge in between. So this option C is correct. If UV is not an edge, so in G, then U is a leaf in T. This condition is always be true. If we remove this must condition from the B option, so then B option will also be a true. If UV is an edge, so for example, if we add these things, if UV is an edge, then V is a descendant of U in T. So this become also a correct. Okay. So option C only.
I think U is a descendant of V.
Descendant U. So what is the meaning of descendant?
Because we are visiting.
U has to be the parent because V is visited after it. I mean,
yes,
it can be another node, but it can't be a descendant of V.
U be the parent, right?
Yeah, V has to be the descendant.
V be the V is a descendant.
Yeah, so U is we are visiting U first, then visiting V. So both possibility are there, B and C.
Sir, B would be correct if instead of must, it would be might, right? Like it is not guaranteed every time
yes,
that
yes.
V
So
will be a descendant.
yeah, if we remove this must term and we just consider that if UV have an edge, if UV is an edge in G, and B is a descendant of U in T.
Got it, sir. Thank you.
Yeah. So this was the last question. So yeah, there are some questions related to the mock, which I think someone is asking.
Yes, sir. 4715.
4715. Okay.
Fourth question, you had given some explanation about it in the last session, but then you said to solve the mock and ask today. So
okay, fourth question is the mock. This one?
Yes, sir.
Yeah, so this is related to the complete graph-based questions. So what we are asking that what will be the maximum or minimum value for n is? Okay.
Yes, sir.
So a connected undirected graph. So here we are using term undirected graph. G has 1081 edge. So here edge is given, and we are asking that number of vertices. What is the possibility of number of vertices here? So for example, if we are taking 1081 edge in our graph, so 1081 edge. So there is one possibility. So for example, if we are creating graph like this, so in the serial order, okay. So vertices will be always be one greater than of this number of edge. Okay. So total number, this is the maximum value. This is the situation if all vertices are connected in the sequential manner like this. So in that case, if number of edge is 1081, so number of vertices will be +1, edge +1. So 1082. This is the maximum value of n possible. Correct?
Yes, sir.
Okay. And now what is the minimum? So we will check that. So for the minimum case, so we will check the option here. So now 47, 46, 47, 46. Okay. So maximum number of what edge are possible in a undirected graph if it is a completed graph. Okay.
Yes, sir.
So in that case, for example, if we take 47, so what will be the maximum number of edge? 47 into 46 divided by 2. This is 23. So if you multiply this, so you will get this 1081. Okay. So this is the possible minimum number of vertices in your graph, and in that case, this graph is a complete graph.
Yes, sir.
So you will get this number of edges, and this is the maximum. This is the maximum possibility when every nodes are connected in this sequential manner. So you can say that the total number of n is maybe less than equal to 1082. This is the maximum things, and less than equal to 47. Here, this is the vertices number. Okay.
Yes, sir.
And next question is
7.
4, 7. Okay. I think we have discussed this.
Yes, sir. I wasn't able to understand it in the last session.
Okay. So 7th question. So 6 you have.
Yes, the 6th I understood.
Okay. So we are starting from, for example, we have one box is open. Okay. And we are just starting from 99. 99 are locks, and we will check all first. So in the first case, we will open 99 box. Okay.
Yes, sir.
Plus 98, then plus 97 in that manner. So this type of things operation, we can say that this is a series like this: n-1 plus n-2.
Sum of first n-1 numbers.
Dot 1. So this type of series actually return the solution
n-1. Yes, sir. N into n-1 by 2.
Okay. So we have the n value is 100 into 99 divided by 2. So this is 50. And so what is the value for that is? So 0, 5, 9, 45. So 545 or 49. Yeah. 4950. What the answer?
And then 10 seconds, because each box takes 10 seconds. Got it, sir. But sir, shouldn't our calculation be from 99 and 98? Because one box is already open.
Yeah, so in the first case, we will open 99. No?
Yes, sir. So aren't we finding the sum of first 99 numbers?
First 99 means?
I mean, our series goes from 99 to 1, right?
Yes, yes.
So if we reverse it, it goes from 1 to 99.
1 to 99.
So that is the sum of first 99 natural numbers. And the formula for that is n into n-1 by 2. So won't that give
n into?
n-1 divided by 2.
Yes.
So won't that be 99 into 98 divided by 2 instead of 199?
Okay, so I think formula for 1 to n minus, so this is the n-1.
Yes, sir, it is n into n plus 1 by 2.
Yeah, that formula is n into n plus 1 by 2.
Right, sir, got it.
Okay, if we are removing this last element, so then it become like
yes, got it.
Yeah. Okay. So what is the answer for this is?
49,500.
Okay, answer is correct, no?
Yes, sir.
Okay. So, and next question is, yeah, 40,
So
yeah,
15.
yeah, I confused was that there is 1 0 missing. Okay, this is correct. So next question is 15. 14 and then 15. Okay, so this is the matrix. So here matrix is sorted. Okay.
Yes, sir.
So what you are thinking about this question? According
So
to
like,
you, what is the correct answer?
So do we have to assume that it is sorted beforehand, or do we have to apply a sorting algorithm on it as well?
No, condition is given. No. So here, what is which the entry of each row are sorted in increasing order from left to right, and the entry of each column are also sorted in increment order from top to bottom, and the first element of each row is greater than the last element. So definitely the list whole matrix is sorted in the snake order, you can say. So like this. So for example, 1, 2, 3, 4, then next element will come here 5, 6, 7, 8, 9, 10, 11, 12, like in this manner, snake order.
Yes,
okay.
Sir.
So if our matrix is sorted in this manner,
yes,
so
sir.
we will apply the first for find the correct row, then we will find the element in that case. So for example, if we are searching, so one row I am more adding, so 13, 14, 15, 16. Okay, so first we will find out the correct row to search again. So we will apply the binary search method on the rows first.
Yes, sir. So we
For
get log n.
example, yeah, for example, we are searching 11. So we will apply the binary search here. And every time searching, we will check the first element and last element.
Yes, sir.
Okay. So for example, if we are checking 11, so we will, so this is 0, 1, 2, 3. So 4 divided by 2. And in log n case, we will find the second index. And in that case, we will read the first element and last element. So this is 9 and 12. And we will check that our searching element is lies in between 9 and 12. If yes, then we will search this row only.
And sir, in this row again, we'll apply binary search.
Yeah, this is row is also sorted, so we will apply the binary search method on the columns.
Got it, sir. Got the
Okay, so
answers.
yeah, so this takes log n and this takes log n. So yeah, here representation is both correct, because we can represent log m plus log n by log m into n. Both are the same.
Yes, sir. Got it.
Okay. Any other question?
No, sir.
From any others? From any others? And one topic, I think I not included any questions. So one pre-post question. So I have discussed this question in the last in our open session of the previous week. So just watch that part, pre-post numbering, and we can identify the cycle things by some condition is given. So just watch these things for pre and post question, pre-post numbering in the DFS tree.
And sir, can we have stack evaluation for the quiz?
Stack evaluation, that is a programming question, no?
Yeah, sir, but sometimes they can ask now, like the remove one element from the final stack and replace it with X and ask us to find the value, something like that, because it's covered in the lectures. So
yeah, so those things are covered in the lectures, can be part of the in your quiz.
Okay, sir.
Okay, so any other study from the other students? Total 12 are there. So already I think 4 hours approx completed. Okay, so all the best for all of you.
Thank you. Thank you.
Okay, so thank you everyone. Bye. Good night.
Sir, could you please cover question 13 as well of the mock? I wasn't able to get one of them.
Okay, 13. So
Yes, sir. The DAG one.
yeah, this one.
Yes, sir.
Yeah, so total number of possible topological order. Okay. Oh, where is the question now? Yeah, so here one condition is given actually. So there is one condition: if 2 appears before, then at the same time 8 must also appear before 9.
Yes, sir.
So these two conditions should be satisfied at the same time.
Yes, sir.
And then find the order or possible order. So one second. Yeah. So what is the diagram? I'm creating here 1, 2, 3, 4, 5, 6, and then 7, then 9, and 8, and 10. So condition is the when 2 appears before what is it?
2
when,
before 3, then 8 before 9.
Yeah. So in our order, if 2 is coming before 3, then 8 should also be coming before 9. So this is the one condition is given. So if 2 is come before 3, then 8 should also come before 9. Okay, so we can manually check this type of thing. So we will start from the node which have integrity 0. Okay, so
Yes,
one we can, after removing 1, we can traverse the 2. Okay, then we can traverse 3. So in this situation, you have to take this also true. Okay.
Yes,
so
sir.
okay, so first, for example, this is true. Then after that you will traverse 4, then you will traverse 5. So this is one possible things. So 6, then you can, after traversing 6, you can traverse either 7 or 9, but
We go for
here
7.
but we have to go for 7, then we have to go 8, then we will come back to the 9, and then 10. Okay, this is the first condition. So there is one other possibility if we can maintain this property in this sequence.
Sir, why can't we go from 8, 10 and 8 to 10 and then back to 6 and then to 9? Because
No,
it doesn't say that it has to be immediately after it, right?
No. We have to check every time. If node have in degree 0, then we can traverse only.
Right. Okay, sir. Right.
Okay. So this is the condition of topological order. So if we are removing this condition, so if, for example, if we take 1, 3, then 2, so then we can take any orders.
Yes, sir.
So 4, then 5, then 6, then we can choose 7, then 8, then 9, then 10. This is the one part. And the same things we can change from here. 6, then we can take 9, and then 7, then 8, then 10. This is also possible. And same things from here. We can traverse 7, then 9, then 8, then 10. This is also correct.
Yes, sir.
And other possibility are there. So 6, 9. Also, so 9. If you have 9, 7, 8, this I have already done. 7, 8, 9 I have already done. 7, 9. Okay, so all these are completed. So what the others possibility is? So 1, 3. Okay, yeah. So other also possible. So for example, if it takes 1, 3, 3, then we can move to 4, then 5, then 2. Okay, then we can, after that we can perform these 3. Correct?
Yes, sir.
So how many numbers have completed now? So 1, 2, 3, 4, 5, 6, 7. 7 is completed. And same things, we can also perform the order 1, 3, 4, then 2, then 5. And then we can perform all these 3.
Yes, sir.
So 7 and 3 is 10. Other possibilities also there. 3, 4, 3, 2. So I think 10 is the answer for that question.
Yes, sir.
So these are the possible.
Sir, could you go back to the workspace once again?
Okay. So
Where you were drawing the graphs?
Yeah, so 10 is answer. Okay. Yeah.
Sir, please scroll down a bit to the place where you branched it out. Yes, sir. Got it, sir. It was a minor mistake on my side. Thank you.
Okay. Okay. So thank you, everyone. Good night, all.
Thank you, sir.
Thank you very much.
Thank you, sir.
Okay.